All right, first of all, said that there is math in chemistry. What makes it sound daunting is the fact that, what makes it seem daunting is the fact that we do math now, but we put a little chemistry spin on it. But it really just boils down to some basic math skills that we just applied to chemistry. All right, so let's just review. We're going to review here really quickly some of the basic things that we expect you to know for the class. And again, in the dynamic study modules on Mastering Chemistry, it kind of walks you through some of these processes. Right, so the dynamic study modules, when you go into them, you don't have to know all of the answers right away. Right? The point of the dynamic study modules is if you don't know something, it walks you through how to solve it. Right? But it works best if you actually read the chapter before you do the dynamic study modules. All right, and like I showed you last week, it kind of adapts to what your background is as you're bringing to the exercise. All right, so look at some basic math skills. The first thing we're going to take a look at is identifying the place digit. Or the place value for each digit in a number. All right, so we have 25, 18. Let's start at the right side. What place does the 8? Is that the ones, tens, hundreds, thousands? That's the ones. What about the 1? That's the tens. And the 5 would be the 100. And then the 2 would be the thousands. All right, so that number is 2,518. So those are for relatively big values. What about smaller values? So we have 6.407. All right, so the 6 here we just saw from the previous one would be the ones. And now we get to the decimal point, and then the places after the decimal point. So that 4 there, immediately after the decimal point, would be that's the 10th, right? So that's 4/10. And then the 0 would be the 100th place. And then 3 places after the decimal point, where the 7 is, would be the 1,000th. Right? So again, keep in mind, it's not, when you go after the decimal point, the first place after the decimal is not tens, it's 10th, 1/10 or tenths. And then the second is hundredths, not hundreds. And the third is thousandths, not thousands. All right, let's do a quick summary here. So this one, okay, so the ones will be which place? Raise your hand. Yes, I saw you raise your hand. The 1 would be the 1. The ones? Try again. Okay, let me rephrase the question to you. What about the 5? What would the 5 be? The 5 would be the ones, right? Okay. What would the 1 be? Yeah. The tens. What about the 2? The 10th. And then the 4 would be the 100th. Okay. All right. So identifying, where the digit lies in the number is going to be important, because when we start dealing with mathematical operations, multiplication, addition, division, etc., we're going to have to apply those or use those things. All right, let's revisit or visit how we work with positive and negative numbers in math. So positive number is any number that is more than 0, and typically there's a positive sign associated with it. Oftentimes, though, that positive sign is just omitted or left out for simplicity's sake. All right, so if you see 8, that automatically assumes that it's positive 8, or sometimes you'll see plus 8 written, just to avoid any confusion. Right? So if you don't see a sign in front of something, we assume that it is positive. So plus 8 is also written as just regular 8. Negative number is a number less than 0, and there's always a negative sign associated with it. All right, so that's positive numbers more than 0, negative numbers less than 0. How we work with these numbers now are going to be important. So when we multiply, let's say two numbers, and one's positive and one's negative, sorry, let me rephrase that. If you multiply two positive numbers or two negative numbers, the answer that we get is always going to be positive, right? So for instance, we can say 8 times 2, all right, that's going to be equal to 16. And you'll notice I don't have any signs in front of any of those numbers, so they're all positive. All right, I'll just put it in this form. Right, so they both mean the same thing. If I have negative 8 and I multiply it by negative 2, right, that would give me what according to that rule? It will give you 16. Negative 16 or positive 16? Positive 16. All right, so we can write it as it is, or if you want to, you can put the positive sign in front. So you multiply two numbers, and if those two numbers have the same sign, whether they're both positive or whether they're both negative, the answer that we get is going to be positive. If you multiply two numbers and they have different signs associated with them, well, then the answer is going to have a negative sign. All right, so if I have 8, so let's say positive 8 times negative 2, right, that's going to give me 16, but my sign now is going to be negative, right? And conversely, if I have negative 2 times positive 8, how about negative 8 times positive 2, right? That's also going to give me negative 16. So when the signs are different, right, the answer there is going to have a negative sign. When we divide numbers that have different signs, it's the same rule as when we multiply them. All right, so the same rule for multiplication is the same as the rule that we use for division. So for instance, if I have 8 divided by 2, all right, that's going to give me 4. If I have negative 8 divided by negative 2, that's also going to give me 4, positive 4. If I have two numbers and they have different signs, so let's say I have negative 8 divided by positive 2, that's going to give me negative 4 as my answer, right? So it's the same rule that we use for multiplication. Am I going through this too quickly? Okay, if you need to slow down, or if there's anything that's confusing, please raise your hand and let me know. And by all means, you can come see me during office hours as well to get it sorted out. What about addition of positive and negative numbers? So if we're adding two positive numbers, right, well, when we add them together, we're going to get a positive value for our answer, right? So 3 and 4, again, the positive sign is understood for both of those. So 3 and 4 is going to give us 7. It becomes trickier when we're adding together two numbers that both have a negative sign. All right, so negative 3 plus negative 4 is going to be equal to what? Negative 7. All right, so it's that you have minus 3 and you take away 4 from that, right? You're going to end up with negative 7 as the answer. So the answer there has a negative sign. If we have a positive number and we add it to a negative number, we just simply subtract the smaller number from the larger number, right? And the result here is going to have the sign as what the larger number is. So 12 added to negative 15 is the same as saying 12 minus 15, which would be equal to what? Negative 3. All right, so the sign of the answer here has the same sign as the larger number, negative. In this case, it's negative. If we go into subtraction, when we have two numbers that are subtracted, we change the sign of the number to be subtracted. So for instance, 12 minus positive 5 is the same as saying 12 minus 5. All right, so these two signs here end up becoming negative. If we have 12 minus minus 5, right, those two become a positive sign. If I have negative 12 and again minus 5, that here becomes a positive sign. And then if I have negative 12 minus positive 5, right, a plus and a minus end up becoming a negative sign. So negative 12 minus 5 would equal negative 17. So it can be a little tricky when you have all of these signs to work with. Right? What can help you through this process is your calculator, right? So these are things, I mean, if math is your thing, you can do this in your head, right? For most of us, math may not be our thing, right? And that's where you want to use a calculator to help double check with what you do in your brain. Now, your calculator is only going to do what you tell it to do. So if you tell it to do something incorrectly, is it going to fix it for you? It's not that powerful, all right? It's not like Siri or Cortana or whatever your device is that you use. So it's important that you know how to use your calculator properly, right? So in your calculator, there's a button that you can use to change the sign, and it's usually a plus minus button. Did you guys bring your calculator to class? If you did, which you should, take it out and let's go through some practice exercises. Depending on the type of calculator that you have, the order in which you enter the numbers and the signs may vary a little bit. But if you have one of the TI-30s, right, it's a little bit easier or not as difficult to enter the operation as compared to some of the old-time calculators where you had to do things in like a reverse order. All right. So what I want you to do, I mean, this thing here kind of walks you through a couple steps. What I want you to do is to do a couple of new ones. So I want you to enter this and figure this out using your calculator. So negative 20 times negative 3. So I want you to enter that into your calculator and tell me what you get. So I'm hearing 60. Negative 60 or positive 60? Positive 60. Right? You should get positive 60 or just simply 60 without any sign in front of it. All right. What about if we had negative 20 plus minus 3? Or negative 20 plus negative 3? Negative 23. Confirmation in the back. Negative 23. Confirmation that way. Negative 23. All right. So when you enter these numbers in your calculator, right? So when you entered this, so who said negative 23 first? Negative 20. So how did you enter this into your calculator?
I have a button that makes it negative.
Okay. All right. So which button makes it negative? The one on the bottom. So it's a plus minus.
No, it's just the minus.
It's just the minus symbol. Okay. So you had negative. So you entered in negative 20, and then you added it. And then you entered negative 3 as well. So just as you just as you see it here, you entered it into your calculator, right? And that's the good thing about the TI-30s, is that you can enter the number and the operation as you see it in your problem. Some of the older type calculators, you have to do it in a reverse way, right? So you shouldn't have those older type calculators, but if you do, all right, you want to make sure that you know how it works. All right. Any questions so far on signs, entering numbers in your simple numbers in your calculator? Calculator use is a very important thing in chemistry, right? And we're going to get a little bit deeper into how we use them, especially when we get to scientific notation in a little bit. All right, the next thing we're going to take a look at here is percentage. And we're going to see percentages down the road when we start looking at different types of solutions and how we represent those solutions in terms of how much of something is in that solution. You see percentages all the time. Right? When you go to the grocery store or the Walmart or wherever and you buy milk, right? What do you reach for? What type of milk do you reach for? There are several choices, right? You can buy whole milk, you can buy 2%, you can buy 1%, well, what does the 1% or 2% or whole milk actually mean? Right, well, it's a percentage, right? That's the first thing. And then in terms of percentage of what, we'll see down the road. So when we talk about a percentage, the ratio that we're looking at in any percentage is always part over whole times 100. Okay, I'm going to write it slightly differently. So the part divided by the entire thing, and because it's a percentage now, percent means out of 100, we're going to times it by 100. Right? That's a general formula by which we calculate percentages. The challenge then is to know what the part and what the whole actually are. All right, so we're given a statement here. We say, or we're told that an aspirin tablet contains 325 mg. That stands for milligrams of aspirin, which is the actual thing in the tablet that relieves pain and inflammation and all that stuff. And that entire tablet itself has a mass of 554 mg or milligrams. What's the percentage of aspirin in this tablet? So, we first of all have to organize the information. All right? We're asked for percentage of aspirin in the tablet, right? So that would suggest then that we need to know how much aspirin we have in the tablet as a whole. So our part here is the aspirin, which is just the ingredient, that part of the thing, and the whole thing is the tablet. Right? And we're just comparing out of that entire tablet, how much of the tablet is aspirin. So if we take those two, and we're given what those amounts are, we have 325 mg of aspirin, that's the part, divided by the whole, which is the tablet, 545. I'm sorry, of the tablet. And then we times it by 100. And what do we get? All of you have your calculators out, so you can do this. 325 divided by 545 equals, and then you times it by 100. $59.6%, right? And this thing here, that means percentage. So our tablet is 59.6% aspirin. That's what percentage or what fraction of the tablet actually contains that active ingredient. The point here is the percentage is always the part over the whole, the entire thing. And you have to know those two in order to calculate the percent of anything, whether it's a tablet or aspirin in a tablet, or whether it's something else. So because the percentage represents, it's always out of 100, we can also go in a slightly different way in terms of how we interpret that information. All right, so for instance, if we are told that we have a sample of these balls and we're told that 8% of that sample is yellow balls, right? What that means, right, again, percentage is out of 100, so this would suggest that there's 8 yellow balls out of how many? Percentage always, it means out of 100, right? So it'll be 8 yellow balls out of 100. That's what that suggests. Not just suggests, but that's what it tells you when you see percent. It's out of 100. So if we go back to the example that I mentioned to you, when you go and you buy milk, all right, and you buy, let's say you buy 2% milk, the good stuff. All right, so 2% milk does anybody know the percent of what it is that you buy when you buy milk? Like what's the part? Cream, close. It's milk fat. Yeah, so it's 2. What this suggests is that there's 2, let's just say grams for a unit, 2 grams of milk fat, and it's percent, so it's out of every 100 grams of the milk itself, right? So every 100 grams of the milk, 2 grams of it is fat, the milk fat. Which means 1% would be out of every 100 grams, 1 gram is milk fat. So percent always out of 100. All right, questions on percentages? Like I said, we're going to see this again in a lot more detail when we get to solutions, and we'll revisit the whole milk thing and some other solutions and other important things that we encounter as well. All right, so the last thing in this subsection that we're going to deal with today is a little bit of manipulating of equations, a little bit of algebra. All right, some of us are really good at manipulating people. In this class, we want to be able to manipulate equations to our advantage. All right, we're going to start with relatively simple equations, and we're going to see more examples of these again when we get down the road in some of the subsequent chapters. All right, so we have here an equation. 2x plus 8 is equal to 14. And here we want to solve this equation for x. So what this means, if we want to solve it for x, right, this means that we want to isolate x on one side. Of the equation. And put everything else on the other side. Right, so we need to get x, doesn't matter which side of the equation, but x, and only x should be on one side. We need to move everything else to the other side. So that involves a little bit of skill, right? How are you going to move everything else to the other side? Well, the first thing we can do, if you notice here, we have 2x plus 8 is equal to 4. So maybe we may want to get rid of this 8 here and move it to that side, right? So when you move things from one side of the equation to the other, for instance, this plus 8, when you move it to that side, you change the sign. So it becomes minus 8. Another way of thinking of it is, in order to just get x by itself, you have to take away 8 from this side. And if you take away 8 from this side, you have to take away 8 from that side because it's an equation. And whatever you do to one side of an equation, you have to do to the other side. Does that make sense? Okay, we want to isolate x, or the term that has x in it, on one side. So we can say then, we can take this positive 8 and move it to that side, so it becomes 2x is equal now to 14 minus 8. Right, we do a little bit of math in our head or in our calculator. 14 minus 8 is 6. All right, so we're close, but we're not quite there. We have 2x now equal to 6. We need to solve just for x. So if I want to get x on the x by itself on the left side, what do I need to do to the 2x? Yeah. I need to divide it by 2. All right, so the 2's can cancel. If I divide the left side by 2, I also have to divide the right side by 2. All right, so I divide this side by 2. So x then is equal to 3. So there are several things that we did there, right? We moved a term from one side to the other. We changed the sign from positive to negative. We divided the left side here by something to make sure that we only ended up with x. Whatever we did to this side, we also did to the other side. Right? Whenever you have an equation, you always want to make sure that you do that. So x here is equal to 3. And when you get an answer, right, and you want to sort of use this for all of the calculations that you do, x equals 3, yay, celebrate. Well, hang on, check your answer. Put x back into the equation and see whether or not it actually satisfies it. So if x is equal to 3, and I put 3 in here, right, so 2 times 3 is 6, plus 8 is equal to 14. Right? You always want to ask yourself at the end, does the answer make sense? And are there things that you can do to check the answer? Getting an answer is the first step, but you always want to double check that it makes sense. All right. Let's take a look at another example. So here I have p subscript 1 times v subscript 1 is equal to p subscript 2 times v subscript 2. And here it is asking you to solve the equation just for this thing. So in other words, I want to isolate p1 on one side of the equation. So what can I do to isolate P1? I just want to have P1 on this side. So when you see these two terms, P1 and V1, does this suggest that they're added together or they're multiplied together? They're multiplied, right? So if I want to get rid of this V1 from this side, I would need to divide it by V1. All right, so if I divide by V1, V subscript 1, well then it can cancel out here. So what do I need to do to the other side? You need to do the same thing to the other side, right? You need to divide that side by V1 as well. So we can, let me just rewrite this. We divide both sides by V1. And by doing that, we get rid of the V1 on the left. So we end up with P1. And then we have P subscript 2, V subscript 2 divided by V1. Right? All of those terms may look very complicated. What's P1? What's V1? Doesn't really matter. Right? You can think of them as being X and Y and Z. We just put some other subscripts in there because we'll actually see this exact equation down the road. And we'll have to do the exact same thing that we just did to it right now. Solve for one of the components of the equation.
Is that the simplified answer?
This is as simple as you can get it, yeah, with P1 on one side. And everything else on the other according to math. Does that make sense? So another thing to keep in mind is, when we go through the content in this class, whether it's reviewing a little bit of math or when we see new stuff, we only have a finite amount of time. So we can only go through maybe a couple of practice problems, right? It's up to you to take the time and to practice some more on your own. So the study modules and the homework are going to force you to do that extra practice. The quizzes are going to test you on that, but you really need to do some extra practice. And there's lots of practice questions in your textbook at the end of the chapter. There's many, many, many practice questions. You don't have to do all of them, but you should do some extras. So it becomes sort of, maybe not second nature to you, but you become more familiar with it. All right. I misspoke when I said earlier that equations were the last part of this section. Graphing is the last part of this section here. And we're going to use graphs. Graphs are actually a very concise way to represent relationships between things. And you can get a lot of information from a graph, but you have to know how to interpret it. Right? You see graphs all the time, whether you're watching the news, you're in the newspaper, magazines, all over the place. And you really need to know, not just in terms of a chemistry sense, but also just in terms of a general, consumer type perspective, how to interpret graphs and what do they actually mean. So let's take a closer look at this particular one. This is from your textbook. And we do have a magnified version of it here. All right, so in any graph that we're going to see in this class, there are going to be two main lines that are drawn. There's a vertical line that we call the y-axis, or the vertical axis, and then there's a horizontal line that we call the x-axis. All right, so we have the y-axis versus the x-axis. And in this case, on the y-axis, it's kind of difficult to see. You have to tilt your head a little bit. We're measuring or recording volume. Right? So that's the label, and any graph that's drawn properly is going to have a label for the axis. And in this case, it's volume. And then on the x-axis here, we have temperature. So this particular graph then, in addition to it being generally y versus x-axis, specifically for this case, it's volume versus temperature. I'm going to abbreviate temperature as temp. Right? So when we refer to graphs, it's y versus the x-axis. In this case, volume versus temperature for whatever. This looks like a balloon. And you'll see at the top of the graph, there's a title, which tells you what the graph is representing, what relationship the graph is showing. And any graph that you generate or you see should have all of these components to it. So when we examine this graph, you'll see these points that are either dots, solid dots or dots with a circle around them. These are actual data points. Right? Whoever generated this graph was able to measure the temperature and see what the volume was of the balloon at those different temperatures. And they were able to put those on the graph and then connect those points with a straight line. So generally, we can say, just by looking at this graph, what happens to the volume when the temperature is going up, right? So in the temperature here, we have 0 degrees, 20, 40, 60, 80, etc. When we increase the temperature, what happens to the volume of the graph, of the balloon? As the temperature goes up, what happens to the volume? So we can say as temperature increases, right? So if we go from 20, let's say, to whatever this is, 50, the volume goes from 24 all the way up to around 26 and a half, right? So the volume goes up as well. So as one goes up, as temperature goes up, the volume goes up. We say then that this is a direct relationship, right? And we're going to see several examples of these different types of relationships, whether it's direct or not direct, down the road when we get to gases. Now, one of the important features of graphs is that we can use the data points, right? So we collect these data points from our experiments that we do. We plot them on the graph, and we just connect those points with a straight line. So what we can do is we can use that graph to actually predict what the volume would be beyond what we actually measured. So for instance, I could just extend my line. Okay, imagine that it's straight with the other one. I know it doesn't look completely straight. But we can use a ruler and just extend this line all the way. And we can then say, well, let's say we increase the temperature beyond what we collected. Let's say we increase it to like 120 over here. We can use that graph to predict what the volume would be at that temperature. All right, so let's say this here was 120. We can just find where 120 is on the graph, and we can extend it all the way up over here, and then where it intersects the line, we can see what temperature it ends up being there on the y-axis. Right, and that process is a fancy word we give to that process. It's called extrapolation. And all that it means is we can use the graph that we already have prepared and just extend it out, and we can predict what the volume would be at temperatures beyond which we actually were able to work with in the lab. So the graphs are very powerful from that perspective as well, right? We can use them as predictive tools. All right, questions on graphs. And again, these are just quick orientations to a little math skill, a little algebra, and a little graphing skills. We'll get a lot more deeper into these things down the road. Okay, questions on graphs, interpreting a graph, y versus x-axis. All right. So let's see, what do we have? About 5 more minutes. We're not done with chapter 1 just yet. We have the last section of chapter 1, which is actually where there's a lot of math involved and dealing with numbers again. Let's see here. And we're going to introduce this today. We're going to finish it up on Wednesday. All right, so we're going to use the full time. And we'll continue with this discussion the next time, but I want to introduce it today. And the last section here of chapter 1 deals with this notation that we use in chemistry, but we also see it in physics and maybe some biology. Not as frequently in biology, but definitely all throughout chemistry and physics. Is this technique known as scientific notation. Has anybody heard the term scientific or exponential notation before? Exponential or scientific notation. So it's it's widely used in chemistry, and why we use it is not just to make your life a living hell, We use it because it is convenient for us to use. It's way more concise than writing out a regular number when those numbers are really, really, really big or when they are really, really, really small. All right, so why do we need to use scientific notation? We use it to represent really big or really small numbers. All right, so we typically wouldn't use scientific notation if we wanted to say, well, there are 48 students in class, right? It takes too much work to convert that to scientific notation than just to say 48. But if we wanted to measure and report the width of a typical human hair, right, we can measure that with the right instrument and say that it's 0.000008 meters, right? So it takes a lot of energy to write that out, or we can say it's 8 times 10 to the negative 6 meters, right? So this here is a number in scientific notation. It's the exact same number as 0.00008. We haven't lost any of that information. We've just converted it into a form that it's supposed to be a little more concise, right? So that's a really small value that we can represent using scientific notation. Conversely, if you were to count the number of hairs on a typical human head, right? I'm not going to use my head as an example, but other people's scalp may have lots of hair on it. 100,000 or maybe even a million hairs are typical. Well, that's the same as saying 1 times 10 to the 5. Right? So here we're using scientific notation to represent a really big number. And it's the same number. We haven't lost any information when we take that 100,000 and we convert it into a number in scientific notation. So you'll notice here there are a couple things common to both of these numbers in scientific notation. There's some number here. In this case, it's 8. In this case, it's 1. It's times, and then we have 10.